one that's interesting, and that is that the price of a slice of pizza and the cost of a subway ride they go up with one another. That they're correlated with one another. So we're going to take a quick look at that if I can find it. Get rid of this. Okay, here we go. Okay, so here we go. Unfortunately, I can't blow that up much. So if you can get it onto your screens or log in on YouTube on GoToMeeting and access it that way, it might be a little bit easier to see. So you can see that it seems like there's a real association between the two of these. These are were data from different years. Okay, depending on how old you are, you remember back to some of these different fairs. Come on, come up. Good. Open and repair. Okay, save. Why not? Okay, so these are actual numbers, at least rough numbers, because of course nobody's really done a real survey of what the average price of pizza is in New York City, but roughly about what the numbers cost. It ends in 2003. You guys interested enough? You can add on to that from that. What's the subway fare now? It's $2.75 now, right? Am I right about that? Still, yeah, hasn't gone up again yet. They're talking about it again, but it hasn't gone up again yet. So at any rate, there's some obvious association here, it seems like, right? I mean, in a lot of years, it was literally the same price. Okay, and then in other years, it varied only slightly. So we really have a feeling here that maybe there's an association between these two. It's doubtful that the MTA is coordinating their price increases with the pizza industry in New York City, right? So when we're looking at a correlation, looking at association between what pizza costs, what subway fare costs, we're not necessarily going to infer that there's any causation here. In other words, nobody suspects the price of pizza causes subway fare to go up, or vice versa. It just happens to be that way. Probably has a lot to do with the price of the cost of living index and so on. Okay, so let's take a closer look at this. One of the things that we can see here is that that this is a very uniquely uniquely close association between these two prices. First way we might ever want to look at this when we suspect that there's an association between two numerical variables is to look at it look at it graphically to see if we see an association. So I'm going to quickly graph this. Okay, I'm going to go to SPSS to do it. Graph. I like to use legacy dialogues. I'm just going to do a simple scatter dot. Now, what is a scatter dot? That's going to take each one of these these values that occur together. The price of pizza in 1960 was 15 cents. The subway fare was 15 cents. I'm going to plot one of these on one axis and the other on the other axis. So pizza becomes the y-axis, for instance, and subway becomes the x value that corresponds with the coordinate that we're going to put in there for 1960. Okay, so I'm going to go ahead and plot this. Okay, now it doesn't matter which one I put in here. So right now, later on, it will begin to matter. I'm going to try and just get into the habit here of like maybe to saying that maybe the cost of the subway fare drives up the cost of pizza. Let's do it that way. Okay, so even though at this stage we're not interested in causality, correlation doesn't mean causality at all. Right now, I'm getting into the habit of thinking my x-axis in the future is going to be my independent variable, my predictor variable, the thing that's going to drive changes in the dependent variable, the y variable. Okay, you guys remember from algebra, y is equal to f of x, function of x. So y is dependent on whatever the values of x is. Okay, so I'm just going to do that just by convention now rather than intention. So we can see that looks like a pretty good correlation. See how these different values. This value is our 15 cents and 15 cents in 1960 and 35 cents and 35 cents and $1.25 and $1.35 and so on and so forth. We can actually see all these values. If you double click into this graph, you can actually modify it, including fitting a line to this graph. Okay, now this line we just fit to this graph is drawn so that all of the differences between the y value, the x value, that we predict on this line. In other words, if the cost of a subway token is $1.50, right? We would predict that the cost of pizza would be somewhere over here, maybe $1.60 or something like that, right? So we go up to this line, and that would be our predicted value going across for the y value. Okay, now we do have some actual values, observed values. For instance, this one right here, right? And that particular value doesn't fall on that line. There's a difference between that value and what the line predicts. Well, unfortunately, a straight line you can draw a straight line between 2 points, but you can't guarantee that it's going to go to all of these points unless it's a perfect correlation. And that's not something we'll ever see very often, right? So this line is drawn so all of these averages difference between our predicted value and our observed values. In other words, between a line and where each one of these values is, how each one of those project the value of y. Each one of those differences are squared and they're balanced. So the sum of the squares of the differences on this side of the line are equal to the sum of the squares on the other side of the line. Now the place where statisticians like to square things, right? So and it all ties into this idea of variance, standard deviation, and so on. So that's how that line is drawn. That's why that particular line is drawn. So as far as correlation is concerned, this looks like a pretty strong correlation. So what does strong correlation mean? Let's go back to our videotape here. Okay, so that's what the outcomes could have been for this particular outcome. So let's say, oops, let's jump up here. Okay, let's say this is going to be our subway ride. X-axis, and of course the pizza was our y-axis. Okay, one of the things we could have seen is that the price of the pizza didn't change for the last 2 years, right? It varied up and down, quite the same, but it randomly varied up and down. Well, the price of the subway token, the price of the subway fare, right, changed over that period of time, went up over that period of time. It doesn't seem to have affected the price of pizza. In this case, we're basically saying there's no correlation, right? Subway fare has no impact on the price of pizza, at least no systematic effect on it. Another way that is just random. There's kind of a cloud according instead as people say up and down or something like that. So this also suggests no correlation. Well, the way that we describe that statistically, there's a calculation. We'll take a little while to describe correlation. Using a statistic called Pearson's correlation, okay, which when the population is rho, summarizes the rho, and for our sample, that statistic that goes along the rho is equal to R, squared to R. Okay, so that value describes how good a correlation this is. So in this case, it's no correlation. So our R, this group of statistics, is equal to 0. So when we're talking later on about null hypothesis, whether or not we have a correlation, we're going to one of the ways that we can describe by words whether or not we have a correlation is that there's no hypothesis, there's no association between the cost of subway fare and the price of pizza. If we were going to put that into terms using symbols for Pearson's correlation, we would say rho is equal to 0 for our null hypothesis, and rho is equal to not equal to 0 for our alternative hypothesis. Okay, so notice that, again, same as before, when you're talking about the population correlation, every person, every value of the population, then you're talking about rho. When you're talking about our statistics, you're talking about R. So what values does rho have, or R have? Okay, so, if we have a strong correlation, something like our subway situation, something like this, with this strong graphic correlation here, we can have values for R that go from -1 to 0 to +1. And 0 represents no correlation. So you can imagine -1 to +1 represent perfect correlation. In this case, our correlation is close to 1, or let's call it 0.9. It's a very strong correlation. So at 0.9 is positive 0.9 because as the X value goes up, Y value goes up. Well, as the independent variable increases, the dependent variable increases as well. That's why the slope of this line is upwards or positive. When we have a negative correlation, we can also have a very strong negative correlation. So R is equal to, say, in this case, -0.9. So if we have a weaker association, maybe something like this, that might be R is equal to -2. So these numbers represent how strong an association is between these two numeric variables. So now we're going to actually calculate this for our pizza example. Okay, let me get back to that. Okay, I can show you a formula for how. So this is a formula for how R is calculated. It's not that exotic. You can see that you have each X value times each Y value, the sum of all of those times the number, these sample size, that might be degrees of freedom or sample size, times the sum of the X's, sum of the Y's, the variability is represented down here, total variability is represented down here. This formula will work out and calculate what R is equal to. And then once you calculate R, you can use that to calculate a statistical significance, the p-value, probability that you'll be wrong if you reject that null hypothesis, that rho is equal to 0. So let's do this because this is calculating the value of R. So I'm going to go up here to analyze, and not surprisingly, there's a value down here for correlate. And in this case, it's two variables, so it's a bivariate correlation. Okay, notice that there's lots of variables in here, and it won't do anything until I add variables. So since we only have two variables in here, obviously, both of them are going in there. So I'm going to click OK. There's a few options checked off here. You don't have to worry about them too much. Pearson's correlation, we want that to be checked off. And we say OK. Okay, so here's our output table. And like many other analyses in SPSS, it runs through every possible permutation, combination of things you might look at. So for instance, we have the cost of a slice of pizza here and the cost of subway fare. Horizontally, here we have the cost of a slice of pizza vertically and the cost of a subway fare vertically. So we have four boxes here. Each time we're comparing one variable to the other variable. Okay, cost of a slice of pizza versus the cost of a slice of pizza. Correlation is 1, right? We're comparing it to each value to itself, 35 cents, 35 cents, $1.35, $1.35. And naturally, same thing happens when we go to this box for subway fare and subway fare, which begs the question, why bother? But that's why SPSS always does this. Right? So now, look at the correlation between the actual cost of pizza over time and the actual cost of the subway fare. And that correlation is equal to 0.9. Very close. Happens to be positive also, right? Now, the second value just repeats that same thing, flips it around. We don't care about that. We're not assuming any causality, so we're perfectly happy with just looking at one of these rather than the other. And in fact, they're always going to be the same anyway. So it's a very strong correlation. Had prices been going down, you get see a negative number in there. Never bigger than 1. Positive 1, never less than negative 1. Okay, so, but that would represent the probability. Now, our significance is going to be equal to, in this case, our two-tailed significance is going to be 0.0000. Again, I mentioned this before, I can't again tonight. Anytime you see this in an MSS calculation, what they're really saying is it's less than 0.001, right? Rather than put in a less than symbol for less than, they just say 0.000. It's not really zero. It's never probabilities are never really zero in most cases anyway. And so, at any rate, so this is a significant result, statistically significant result, right? We don't know how important this result is, but it's a statistically significant result. So now we can go beyond this. We started discussing that not only this information to determine whether there's an association or not, but now we can further and can quantify the strength of that association and how that association works. And the way we're going to do that is we're going to perform a regression. The term regression, remember, the term regression comes from, it's kind of because regression working on this theory of regression mean or something like that. It was a story where they're studying whether 2 tall parents would have a 12 child. That was their same. And it turns out that 2 very tall parents were unlikely to have a child that's the same height as they are taller. He's more likely closer to the mean. So you, right, and in doing that, you develop. That's why it's called regression. And although the name really doesn't have, I don't think, have much to do with the way it's used now. So at any rate, that's kind of like the t-test being associated with here, right? It's a nice story, but oh, oh, that's I like that. That makes sense. That really does make sense. Yeah. Okay, I like that. That is kind of a regression to the mean, right? Exactly, makes sense. Okay, so now we want to use this regression allows us to use this relationship now. How the way we understand this relationship is the tester as well. Okay, so now the way we're going to do this is that we're going to perform a linear regression. I'm going to go to analyze. And one other thing I might mention is there's a lot of different kinds of a lot of different kinds of correlations. And the only thing we deal with here is linear regressions, right? So you can always have associations that are real, but say something like this, right? So maybe that's a asymptotic or an exponential relationship between x and y. Okay, of course, there's sometimes that this is not linear relationship. However, sometimes you can work with this and turn it into a linear relationship. So, for instance, if you made this log y, logarithm of y, this might actually be a straight line at that point, and you can apply this. That might come up occasionally as well. But for the most part, we're still sticking with linear relationships. Okay, so let's calculate, let's recalculate the correlation now, except now we're going to assume that there is some association. I'm going to drop this. There is no association. And maybe open up a file where they're likely to be one. Open data. And let's see what I have here. Okay, violent crime. State by state. This file is on black right now if you want to open it and work with me. So the variables here have 50 states, data for 50 states, and we have the number of violent crimes over some period of time, I guess per period of time per 100,000 population. The number of murders per 100,000 population, the poverty rate as a percentage, the percentage of residents that graduated high school, adults that graduated high school, the percentage that had some college, the percentage of single-parent households in that state, the unemployment record rate in that state, and the percentage that live in metropolitan areas as opposed to rural areas. So, for instance, if we look at Alaska, it's only 41% live in cities, and if we look in Connecticut, 95% lives in cities. Okay, so we have a series of numerical variables here that we might be able to look for an association. Anybody want to propose one? How about murder rate? Say I want to control the murder rate. Which of these other variables you think I might want to look at? Any ideas? Okay, let's try poverty. Good enough. Okay, so let's say analyze. Well, first of all, what did I say was the first thing I usually do? Graphs, right? Let's graph it, see if we see an association. That's that. Okay, and I'm going to move poverty into or murder rate into our y-axis and poverty into our x-axis. Why did I do that? Why did I put poverty into the x-axis? Because we're looking for things that influence the income, right? So I'm starting to examine whether poverty is associated with is causal to the murder rate. In other words, it has some impact. Some change in poverty might have an impact on the murder rate. So I decided to put it into the x-axis. The x-axis is our predictor, our independent variable. In other words, it's going to act on our dependent variable, y-axis. So I'm going to click OK. You can edit the graph in there if you wanted to ahead of time. Give it a title, so and so forth. So what do you guys think? Is there an association or correlation?
No.
It doesn't look good. Everybody says that in this graph. But let's take a look. Let's see. Oh, look at that. Let's take a closer look. Okay, look at the lower end here, the lower poverty states. Aren't the murder rates there lower than the higher poverty states? I double-clicked into it. There's going to be other ways for me to do this as well. The graphs are editable. Okay, let me get this out of the way. Yeah, there it is. I double-click on it, it opens up the graph. Among that, I can do some operations, mathematical operations, like add a fit line like here that I did when I clicked. You can also highlight things, change colors, highlight, edit, add the text and so on and so forth, add labels and so on. So there's a way to edit the report and double click into it. And then when you close it, it saves those changes to the chart. Okay, so now this line represents our correlation, our regression line. Okay, and that line is balanced so that the squares of all of the differences between the lines of each individual value are balanced on each side of this line. There is the one that looks like an outlier. It's actually not that bad an outlier because there's another. I removed Washington, D.C. because it was murder rate at the time that these states together was so much higher. It was an outlier that really skewed the data quite a bit. Okay, so I'm going to go back here. I'm going to go to, since I'm satisfied there might be some association, right? And we're going to see how strong an association in a minute. Say analyze, let's say correlate by variable, and let's take a look at what the Pearson's R value is. Oops, got it wrong. Poverty. Okay, what's the R value? I'll move this up. Okay, it's 0.427. What would you say about this? There's some association, right? Apparent association. This is a strong association. Maybe not so strong, but there is some association. Is it statistically significant? That's 0.002. Right, so it's less than 0.05, so it's significant. And so I can go ahead and say, well, gee, there does appear to be some association between these two. Okay, so I'll establish a hypothesis now and say rho is equal to 0, but I can reject that because I have evidence now that there is a association between these two variables. Take the next step. Analyze. Bless you. Analyze. Regression. Linear regression. And again, I'm going to put our murder rate into our dependent variable and our poverty rate into our independent variable. For now, if you see that little term enter there, just stick with that for the time being. At some point in the future, you might have some issues with that. Okay, so let's go ahead and do this analysis. Okay, as we assess this analysis, notice the significance still the same, 0.002. And here's our R value. It's exactly the same as we just calculated. Right? SPSS also calculates the value for R squared. It actually calculates our variance difference in total variance and calculates that R square, but in fact it's the same thing as just squaring that value of R. Since R was 0.427, R squared is 0.18. Okay, so now look at what that means. 18% of the variability in the murder rate, 18% of the total variability in the murder rate, remember the total sum squares of variability, 18% of that variability can be attributed to the poverty. Well, that's interesting. I know that something that contributes 18% of the murder rate in these various states. That's good. If you think about it, maybe it's not quite so good, because what does that tell you about the rest of the variability? Right? There's 8% variability somewhere else, right? That's not associated with the poverty. So it's kind of a good thing, but we understand it a little bit better. Okay, well, if I go down here, I see a set of coefficients, and you guys remember that. Go back here. Okay, let's go back here. Let's talk about this line we just created. Okay, anytime I draw a straight line, if I put 2 points down here, I can draw, there's a single straight line that can be drawn between any 2 points. There's no other line that can be drawn between those 2 points. If I only have 1 point, well then, if I don't have a second point, what will allow me to draw a line is if I know the slope of that line. So if I know 2 points on the line, or if I know 1 point and the slope of that line, I know that line. I know where that line, how that line has to be drawn. Okay, in our case, the coefficients that we just generated tell me 1 point on that line. See that constant there under B? That constant, which is 0.432, is the y-intercept for this line. What's the y-intercept? The y-intercept is where the line crosses the value 0 for x. Right? Across that's where that line crosses the value 0. It crosses the y-axis. Okay, so that y-intercept is our first point, and is a point. And this other value, this other coefficient for poverty, 0.365, represents the slope of the line. So for every value of 1x that this increases, it increases 0.365. Right, and 1.365. So this looks something roughly like this. Okay, now you got to be a little bit careful because our actual, let's say that this is the rate. I forget what the value of these numbers were. I'm gonna wait for this for the purposes of this. Let's go to the rate 5 to 50 per 100,000 for all the different states. Well, maybe the and up, get a little sloppy there, and so on. But all of the values are in here, right? Well, our correlation, our regression really applies to areas of this line that we have data on. Very often, you'll find that this y-intercept gives you a result that really doesn't make sense. You're extending beyond the meaningful area of regression. Okay, so for instance, if I were going to correlate, let's say, I'm going to wait on that until I'm going to do another one. That'll come up. But it's not unusual to get a value, let's say, for a y-intercept, which might be a negative number, which would be meaningless, like a weight of an infant that's less than 0, something like that, for a certain number of weeks of gestation or something like that. Like we only had data for gestation in the last 60 weeks, right? We might find track of that. We say it's waiting for track of that. We might find that our formula line suggests that the weight of a baby when it's 1 week old is 50 grams or something like that, right? Because it's outside of that range. It really is meaningless. So don't worry about that when that y-intercept doesn't do anything. Okay, so, but we need it in order to draw that line. Okay, so and to calculate our values for our dependent variable. So now, what do these numbers represent now? They represent a prediction of what the actual value is of the dependent variable based on what the independent variable is. So in our case, snug it up here so I can write it down. In our case, when you took algebra, your professor probably told you that the formula for shipping line is y is equal to mx plus b. The statistician's version of that is y is equal to beta 0 plus beta x plus, I guess that's epsilon. I guess this is your error. This is that error. The difference between what the line index and what the actual value is. We're going to ignore that. We're just going to be plotting this line. Okay. So notice that this is just B1 X. Yeah. Okay. BIX. Okay, so you can see B0 here is just another way of saying our y-intercept, and B1 is. So in our case, our formula is, what's that? Yeah, okay. Yeah. Okay, so let's see what we have. We have y-intercept is 0.432 plus 0.365, our slope, times x. So, in other words, our murder rate, we're predicting in this formula, it's going to be equal to 0.432 plus 0.365 times the value times the poverty rate, okay, which is a percentage. So, at any rate, we can use this now to predict our murder rate. It's not going to be very reliable. We're going to have some pretty big errors here. And those errors, if this is working right, are going to be kind of random. Sometimes it'll be higher and sometimes lower. But we don't have, it's not very good predictive. We want to individually calculate, for instance, what if we have a statement of a murder rate, a poverty rate of 10%? Okay, what do we predict our murder rate is going to be? We're predicting our murder rate is going to be equal to 0.432 plus 3.65. Is that right? Yeah, that's right. Okay, so we're predicting our murder rate is going to be about roughly 400,000. Okay, we can go back and we can actually plot that. In fact, one of the other things we can do with SPSS is we can now, let's see if I can find it, analyze. I'm going to go back to regression in here. And I can tell SPSS to, I'm going to click into this button that says save. I can ask SPSS to calculate the predicted value for each value of X. In other words, go ahead and do the same thing I just did now with 10% probability. Do it for each one of the values that we have already. And one of the reasons we want to do that is because we might want to compare what the errors are, predicted value. And so I'm going to click, give me the residuals as well, unstandardized residuals. We'll talk about that in a second, maybe. Not much time left. Okay, and I'll click OK. Okay, SPSS now creates two new variables. And those two new variables are our predicted values and our residual values, how large our error is. Okay, so let's see what this looks like. Our predicted value, let's see, poverty rate, 14%. The murder rate is 7.4. So in this particular instance, our formula would have predicted that our murder rate for that state that has a poverty rate of 14.7 would be 5.8. Okay, so we underestimated it based on our formula. So our residual, the size of our error is 1.6 murders per 100,000. Okay, and so on and so forth. Notice some of them we under-predicted, some of them we over-predicted. Now, if this error is also based on chance, what should we see with these residual values of these errors? What kind of distribution should we get? If it's only based on whether they're more or less, it's only based on chance, and not some systematic error. What do you think? When you have something working all sorts of chance, with chance, when you have a population and it's based, differences are based on chance, and you expect that the extreme values are less likely than the less extreme values, and things towards the middle, we expect a normal distribution. So one of the things we might want to do here is graph that. Can I do it from here? Well, actually, let's do it this way. Analyze, descriptive statistics, explore, and I'm going to take our new variable and standardize residuals. I'm going to ask it to plot histogram for me. See what the histogram looks like. Oops. Okay, that looks pretty normal, right? So that would suggest that the errors are due to chance, and that we're in pretty good shape with our predicting. So now I'm going to go back here. Somebody give me a different variable that you think might influence the murder rate. What do you think? How about the percentage of single parent households? Right, let's give that a try. Or maybe not. Maybe let's try unemployment. Let's try that one first. Analyze, descriptive statistics. Oops. Regression. This time, examine relationship between the percentage of single parent households and the murder rate. And I'm going to click OK. See how that looks. Okay, so now our value, I normally would want to see what the graph looked like, see if there were any outliers, see if one of the things I wanted to point out before was that if you can imagine, one of the reasons I'm interested in looking at it graphically is because let's say we have a situation like this. Here is our values, and so we have a nice situation here with a pretty tight correlation. There's our line, our correlation line, and if I get a outlier that winds up being in the middle of our range of data, like over here, what's that going to do? That's going to take that whole line and shift it up. Right? A little bit. The slope's going to be the same. It's kind of you can see it kind of like pull it up. Now, what if that outlier, instead of being here, that outlier were up? What would that do to my slope? It'd pull it down. So I'm concerned about outliers that are on either extreme because I'm really more interested usually in the slope than necessarily what the y-intercept is. We need the y-intercept as part of our formula to calculate values. Slope tells us something important. It tells us if I am able to control one of the variables like poverty by that much, how much will it affect the murder rate? So the slope helps us predict. Well, if I want to take intervention, should I try and reduce poverty? Should I try and give more support to single parent homes? Should I try and where should that public health money be spent? Because that's the essence of regression is that it quantifies how one variable impacts another variable. So you can make judgments about where you can best do interventions. Okay, so let's take a look at it. So I'm going to do analyze. Did I do it yet? I didn't do it yet. Linear. I'm taking cold medicine. Oh, here's I'm a little foggy here. Okay. So I'm going to save that one for now. I'm going to say okay. Okay, see how unemployment rate impacts this. Okay, the R value is 0.351. Okay, was that better? That's not even as good, right? It's not even as predictive as our poverty rate. And what is it significant? And it's now also significant 0.2. So it is significant. Okay, so but it's not. I can create a formula now. Let's see. Let's see where I'm here. Okay, our formula now is going to be the murder rate is equal to 0.972 plus 0.93 times the unemployment rate. Okay, it gives us a formula that helps us predict the murder rate and figure out what the unemployment rate is. I'm going to ask you now do a correlation between murder rate and single parent households. Okay, I'll give you a minute to do it, and then we'll work on it together. Okay? Again, you need to analyze, regression, linear, for starters. I don't know what that was, but and single parent percentage of single parent households. See what that takes. Again, murder rate is our dependent variable. That's the variable. That's the variable we're trying to predict. And our predictor variable or independent variable is it goes into the X box here, and that one is going to be percentage of single parent households. Better or worse? Better or worse? So guys online, let's see how guys online do. Guys online, better or worse? Oh no, now they've been talking about an echo. Yeah, I tried to use unfortunately, I tried to use the microphone. I didn't realize that I asked earlier, but I guess I didn't wait long enough to get feedback. Unless maybe the echo is coming from somebody that has a microphone. Oh, yep, that's what we got. Somebody's got a microphone on. Okay, the echo should be gone now. I don't think it was the speaker in here. Is the echo gone now? Yep. Okay, that's what it was. I wasn't keeping an eye on you guys. Somebody logged on and turned on their mic. Did you hear ambulances and the arguments in the background while they were on? Dogs barking, wolves howling. Okay, I'm going to go ahead and work on this. How about you guys? What's your opinion? Better? I know some of you guys have done this. Okay, I say okay. I mean, physically do this with SPSS. It's not going to be hard, right? Okay, so let's see. Our R value is 0.677. That's a much stronger correlation than we saw before. Our R square value is 0.459, about 46%, 0.46, right? What does that mean? That means 46% of the variability in the murder rate can be predicted by the percentage of single parent household in the state. That's pretty significant, right? Half of the murder rate can be predicted by this one variable, right? So that's much more significant than the others. Now, I haven't gone through all the other variables, but there may be some combination of variables here that maybe will fill in, maybe will inform what the rest of the variability is. So let's see what happens if I add to that. Okay. Just so you can see the let's see. Okay, again, the formula is going to be the murder rate is equal to negative 8.2. In other words, if the single parent household, rated single parent household is 0, there's no single parent households in a state, then the murder rate would be equal to the y-intercept, which is negative 8.2. In other words, no single parent households, 6 people will appear out of nowhere out of every 100,000, a murder rate of negative 8. So that doesn't make any sense, of course. That's why I'm saying you guys work within the range that the data actually represents. Okay, so let's take a look at that. And the slope again was 0.56. So our formula murder rate is going to be equal to negative 8.2 plus 0.56 times the percentage of single parent households in that community. Okay, and it's a statistically significant outcome. Okay, so now we can combine some of these. Analyze, regression, linear. I'm not going to have time to go through many of these. I'm just going to take another one of these and then move in the variable lives in a metropolitan area. Single parent household lives in a metropolitan area. And I'm going to see if adding that variable into our, what am I doing here? I'm actually creating a little bit more complicated relationship. So now, instead of using a single variable to help predict, a single second variable to help predict my murder rate, I'm saying my murder rate now is going to be equal to the y-intercept plus the slope for this variable x plus the slope for a second variable x, x2. Let's call it x1. Say x and x1. Okay, so I have two slopes, two values now that are going to help me determine what my murder rate is. Whoops, where is it? Did I ever find it up? Yeah, there it is. Okay. Okay. So let's see where we are now. Our R value has gone up again, right? And our R square value now is over 50%. Now there's a little bit of kicker here, right? What did Levi say about multiple linear regressions? Which one of those values should I use? Right? Because there's likely to be some association, because there may be some association between being a single parent and living in a metropolitan area rather than being a single parent and living in a rural area. Maybe single parents can manage better in metropolitan areas and more support and so on and so forth. So there may be some association with these variables that they're not really independently predicting the murder rate, but there's some associate. One influences the other as well. So instead of using R squared, 0.507, to predict how much of the variability I'm controlling for, I'm going to use the adjusted R squared, 0.486. Still better than we had with just a single variable.